Time travel is generally perceived as a concept in theory and science fiction. However, is it conceivable in reality? What does physics teach us about time travel? Is it possible to travel to the past or the future? Neil deGrasse Tyson explains the concept of time and the paradoxes of time travel in some ways. We're already traveling through time, it's just that we happen to be prisoners of the present in the eternal transition from the past to the future. If you travel fast enough, you can actually leap forward in time. Relativity states that if you travel at a significant fraction of the speed of light, time will tick more slowly for you than for all your loved ones back on Earth. If your journey is too long, you might be gone for just a few years while everyone else on Earth ages 100 years. In that case, you've effectively traveled into the future, and everyone you knew when you left is now dead. If you want to travel into the past, that's a bit more problematic. Some people have studied the severely distorted fabric of spacetime to understand its effects on the passage of time. It turns out that there is a way you can take advantage of two moving black holes that haven't quite collided yet, which could allow you to end up in the past relative to when you began that journey. Backward time travel, according to calculations from Einstein's general relativity, is enabled by this severely warped fabric of spacetime, such as what you'd get with black holes coming into close proximity. There are several physical theories that can help us understand what time travel is and how it might work. In 1905, Albert Einstein published the first part of his theory of relativity, known as special relativity. This theory showed that particles of light, photons, travel through a vacuum at a constant speed of around 300,000 kilometers per second, a speed that is extremely difficult to achieve and impossible to surpass. However, throughout space, from black holes to our near-Earth environment, particles are, in fact, being accelerated to incredible speeds, some even reaching 99.9% of the speed of light. Einstein then published another paper in 1915 known as general relativity. These theories are among the most important in all of physics. According to Einstein's theory of general relativity, gravity bends spacetime, causing the passage of time to slow down. In his theory of special relativity, time slows down or speeds up depending on how fast you move relative to something else. For an observer in an inertial frame of reference, a clock that is moving relative to them will be measured to tick more slowly than a clock that is at rest in their frame of reference. This phenomenon is sometimes called special relativistic time dilation. Time dilation can also be considered a limited form of time travel into the future. The faster the relative velocity, the greater the time dilation between the two parties, with the rate of time reaching zero as one approaches the speed of light. Scientists have conducted several experiments to demonstrate that this is true. For example, there was an experiment that used two clocks set to exactly the same time. One clock stayed on Earth, while the other flew in a plane in the same direction as Earth's rotation. After the plane flew around the world, scientists compared the two clocks. The clock on the fast plane was slightly behind the clock on the ground, meaning the clock on the plane was traveling slightly slower in time. Another famous experiment is the twin paradox, which, according to Neil deGrasse Tyson, is not a paradox at all. He describes it as a hypothetical scenario using identical twins to illustrate Einstein's theory of relativity. Take Newton's laws, for example. He has a law of motion and a law of gravity. Then we find out, wait a minute, if there's a high gravity source, Newton's laws fail. If you're moving super fast, faster than a galloping horse, whatever Newton may have experienced in his life, his equations start to break down. Do you discard all of Newton? No, it works in all other cases. So what's going on? Einstein creates new laws of motion with his special theory of relativity. Einstein also develops a new law of gravity, his general theory of relativity. Do they replace Newton? No, they draw a larger circle around the applicability of Newton's laws. Newton's laws apply here, and Einstein's laws take over. However, even with Einstein, his equations can't take us to the center of a black hole or explain the singularity at the beginning of the universe. We know now that his theories fail at those points, they blow up on the page. So, we have a whole new frontier of science, with string theorists and the best minds working on extending Einstein's laws into an even larger framework that can explain everything in our universe, not just most things. Many scientists have proposed time travel theories that describe how time travel might be possible. Physicist Miguel Alcubierre proposed a theoretical solution to Einstein's equations, which would allow a spacecraft to achieve apparent faster-than-light travel. If a configurable energy density field lower than that of a vacuum could be created, a spacecraft wouldn't need to exceed the speed of light in a local reference frame. Instead, the ship would traverse distances by contracting space in front of it and expanding space behind it, resulting in effective faster-than-light travel. Objects can't accelerate to the speed of light in normal spacetime, but the Alcubierre drive manipulates space around an object so that it would appear at its destination more quickly than light would in normal space, without violating any physical laws. However, the proposed mechanism of the Alcubierre drive requires a negative energy density and exotic matter, which would violate known laws of physics. This leads people to think that traveling back in time can't happen in our universe. The famous grandfather paradox illustrates time travel's contradictions. A person goes back in time and kills their own grandfather before the conception of their parent, which would prevent the time traveler's own existence. There are some ideas about how to travel into the past without creating such paradoxes. One theory suggests you could travel on a space-time trajectory that doesn't intersect with your own timeline, so you can't alter your own past. However, executing this would require enormous energy, far beyond what we can currently harness, especially since we're still extracting oil from the ground. The simplest way to travel into the future, though, is by traveling extremely fast, much faster than any technology we've developed so far. Most studies on time travel rely on classical general relativity, and creating a quantum version of time travel requires physicists to figure out time evolution equations for density states in the presence of closed time-like curves. In Einstein's theory, a closed time-like curve is a curve in spacetime that could be traced back in time but not forward. In 1991, physicist David Deutsch at the University of Oxford proposed a solution for time evolution equations that could resolve the grandfather paradox and nondeterminism. However, his resolution, which involves the time traveler entering a parallel universe, is considered unsatisfactory by some since it suggests that the quantum state is a superposition of states where the time traveler both does and doesn't exist. Another principle, developed by Russian physicist Igor Novikov in the 1980s, offers a view of how backward time travel could be possible without generating paradoxes. According to this theory, physics in or near closed time-like curves must be consistent with the universal laws of physics, meaning self-consistent events are the only ones that can occur. A time traveler's actions in the past must have always been a part of history from the beginning, so they could never actually prevent their time travel from occurring, as that would create an inconsistency. While some physicists debate whether time travel is possible, theoretical physicist Carlo Rovelli suggests that time itself is an illusion, and that our universe is simply a complex network of events into which we project the sequences of past, present, and future. The entire universe obeys the laws of quantum mechanics and thermodynamics, from which time emerges. Thank you for watching. Did you like this video? If so, show your support by subscribing, ringing the bell, and enabling notifications so you never miss videos like this one.